Hello everyone, I'm Mark.
Hello everyone, I'm Naveed.
Hey guys, I'm Shahid.
Hello everyone, I'm Shoyo.
And we are
the
Rattz. Today guys, we're going to talk about simple harmonic motion. My colleagues here will guide you through the video. Please stick with us till the end of the video. Thank you so much.
Thanks.
Welcome all. We hope you're happy. We hope you're ready for a wonderful physics lesson. I have my partner with me, and today we're going to give you some brief knowledge about SHM, or simple harmonic motion. So today we have our pendulum setup. Later we will have one of our colleagues will also explain the same concept with a spring setup. So first we need to know what SHM is, and SHM stands for simple harmonic motion. Two necessary conditions you need to know that I'll explain later is that in simple harmonic motion, Hooke's law, which will also be explained, must be respected, and the force and the net force must always act towards what is called the equilibrium point. So let me take you straight to the setup. As you can see, our setup isn't moving, it's stationary. And right now, this is the midpoint or the equilibrium point. So all forces will always act towards here. So if I was to have my setup here, Naveed can set it up. So at this point, this is what we call the amplitude, or this is the amplitude, or like the maximum displacement that one can achieve in such a setup. So all forces will act towards the midpoint, so Naveed will let go of the pendulum. As you can see, when you launch it from here, it always pass here to come up here. And when it starts from here, it's also going back like this. So with respect to slow motion, this is how it's moving. It's coming back to the equilibrium point, it's going up, and it's coming back down, and it's going back up. Another important condition you need to know is that where the pendulum starts is where it must come back for simple harmonic motion to have taken place. So saying that if it started here, it will go like this, come like this, and end up back here. So let me demonstrate it without slow motion. As you can see, it came back. So what have you noticed? One, we notice that whenever we start from here, it will travel like this and come back like this. This is what we call period. And I would also like to talk about the energy in simple harmonic motion. Now, first of all, I hope we are familiar with energy. I'll just explain it again. Energy is the ability to do work. In simple harmonic motion, we will focus on only two types of energy. That is potential energy and kinetic energy. For you to understand kinetic energy, it always relates, it is the energy an object has in respect to its position. So whenever you hear potential energy, always think about position. Now, let's go into our setup. Over here, we can see that the pendulum is at a higher position than it was at the equilibrium point. We need to going back to our definition of potential energy, where we have energy in respect to position. So at this position, our potential energy is maximum. And going back to kinetic energy, where it is energy in respect to motion. So whenever you think of movement, always think of kinetic energy. So back here, we have maximum potential energy and we have zero kinetic energy. So your total energy at maximum amplitude will be potential energy plus zero. So in the end, we can say total energy at maximum amplitude will be equals to potential energy. As we go down, our position is decreasing, our amplitude is decreasing. So as that happens, potential energy is decreasing, but you notice that as we're going down, movement is taking place. So as you've seen, movement is taking place. So that means our kinetic energy is going to increase. So as we go down, KE or kinetic energy is increasing, but our potential energy is decreasing. And once we get to the midpoint or the equilibrium point, our potential energy is zero, because this is at lowest amplitude in respect to potential energy. But our kinetic energy is maximum. So the total energy of the system at this point will simply be equal to KE or kinetic energy, whose formula is a half mass times velocity squared. A brief recap, I will state again that period is the time taken for one complete oscillation. That means from here to here and here, going back here, back to its original position.
One period. Frequency
Will be defined as number of oscillations per second. So frequency will be 1 over the period. Or
1 by t.
Or 1 over t. And lastly, energy in an SHM system, we only have potential energy and kinetic energy. At maximum amplitude, always remember that PE is max and that there is no kinetic energy at this point. At the equilibrium point, we have maximum kinetic energy and zero potential energy. And at another maximum amplitude point, same thing, maximum PE, zero KE. We hope that this short setup will help improve your understanding of simple harmonic motion, and we hope that you will learn to love physics
as much as we do.
It's not hard, you just have to read, understand the concept, and practice, and you'll be good. So from me and Navid, we'd like to say thank you to our viewers. We hope that you will take something home with you in respect to physics. Thank you.
Thank you.
So let's examine another example of simple harmonic motion. We have a spring here, we have some masses. So the surface is stationary, it's not moving. So this is a perfect ideal situation. So we have a spring here, and as I move the masses downwards, so what is happening is that as the masses move up and down, in an ideal situation, the elastic potential energy is at its maximum, given that the surface is frictionless, and kinetic energy is at its maximum when the block is in the middle. So what is happening here is that the spring is exerting a force here, and it's trying to put the blocks at an equilibrium here. Now we have different types of springs. Some are loose, some are stiff. This property of springs is what we call a spring constant. The force exerted is equal to the negative spring constant multiplied by the displacement of the objects. So we have the force. Spring constant is negative because it's moving in the opposite direction of the force exerted. X is simply the displacement of the objects. And this formula is what makes up the Hooke's law.
Hey guys, I hope you understood what my colleagues were trying to explain and you take something home with you today. Thank you for sticking with us to the end of the video. That's all from Rattz. Thank you.
Thank you.